is a language hierarchy that is known as Chomsky's hierarchy. So, it is defined by Noam Chomsky. So, according to Chomsky, there are 4 types of languages. They are known as type 0, type 1, type 2 and type 3. So, out of these, type 0 is the most flexible class of languages, because the corresponding grammar that we have is known as free grammar. So, this is called free grammar, and the successive classes or successive types, so they are more and more restrictive in nature. So, type 3 is the most restrictive version, which is known as regular languages, and the corresponding grammar is called regular grammar. Okay. Then we have got type 2. So, type 2 is known as context free grammar, context free languages, and the corresponding grammar is called context free grammar. And this type 1 is more less constrained compared to type 2. So, they are known as context sensitive grammar or context sensitive language. So, from the name we can understand that this free grammar, it can accommodate all other types of languages, but as we are going from type 0 towards type 3, the languages are becoming more and more restrictive in nature. So, for each of these class of languages, so we can have different types of acceptors available from the automata theory or the computation theory, and this for the regular grammar we have got the finite state automata. So, the finite state machine or finite automata. So, this is the class of that this particular tool can accept type 3 languages. So, we have got examples like this NFA, DFA, etc. So, all the regular expressions that we have seen in our discussion during lexical analysis, they belong to this type 3 language, and we can have the corresponding regular expression. So, we can draw the corresponding NFA or DFA, and also we can write down the grammar in some form. So, I will come to that slightly later. Then in the context free category, so here the corresponding acceptor is known as push down automata. Push down automata. So, this is basically apart from the finite state machine. So, you will need a stack for designing an acceptor for the type 2 languages. So, they are known as push down automata. Similarly, in context sensitive category, we have got linear bounded automata, which can be used for designing acceptor for this type 1 language, and this type 0 or free grammar. So, here we have got Turing machine. Okay. So, as the acceptor machine that can detect whether a given string belongs to the particular language or not. So, that can be done, that can be constructed using Turing machine for free grammar. Now, out of all these machines, Turing machine is the most generic one, and naturally we can so that is going to be most powerful. However, constructing Turing machine, as you know, the Turing machine is a hypothetical machine. So, we cannot construct it because practically because the tape size is going to be infinite. So, this is a theoretical machine only, but it is the most powerful computation platform that we can think about. And as we go from this towards this finite automata, they become more and more restrictive in nature, and the corresponding acceptor, they becomes easier to design. Now, let us look into the corresponding grammar, like we will start with the regular grammar and then slowly go to the other category. So, regular grammar, we can have grammar rules of the form x producing A or x producing A y, where x y. So, these are non terminal symbols. So, these are they belong to the class Vn, that is the class set of non terminals, and A is a terminal symbol. So, A is a terminal symbol belonging to the set Vt. Okay. So, the all grammar rules will be of this form x producing A or x producing A y. If you can take an example, like suppose I have got a got an example like this, say x producing epsilon, x producing A or A y, and y producing B. Now, you see that here all the production rules, on the left hand side we have got a single non terminal, on the right hand side we have got a single terminal symbol or a single terminal followed by a non terminal. So, either these two combinations. So, if a grammar is like this, then we will tell that the grammar is a regular grammar. So, we can quickly try to understand what is this grammar. So, you can see that this grammar, it will accept all those languages that can have at most one B, and that and the B, if the B is there, so it will appear only at the end. Like I can have strings like say A, B. So, this can be derived starting like this, x producing A y, then sorry, it is not A, B. So, I can have the strings are x producing A or A y, and y may be replaced by B. So, I can have a single A or the string A B. So, only these two. So, these two is the languages, these two are the strings belonging to the language. Now, so this is an example of context free, sorry, this is an example of regular grammar, and they are the type 3 grammar, and the corresponding language is the type 3 language. Next, we will look into context free grammar. So, in a context free grammar, so all production left hand side it will have a single non terminal. So, here the idea is that left hand side of all production will have single non terminal, single non terminal symbol. So, typical examples are like this. I can have say x producing A y z like this, where x y z. So, these are non terminals and A is a terminal. So, on the right hand side there is no restriction. So, another rule may be say y A z. So, like that I can have a number of rules. So, on the right hand side we do not have any restriction, but on the left hand side there is only a single non terminal symbol. So, if the grammar can be specified by means of production rules like this, then the grammar will be called a type 2 grammar or context free grammar, and the corresponding language will be context free language. And as I have told in the last class that most of the programming language constructs, they belong to this type 2 category. So, most of the grammars that we will be using for this different programming languages, so they follow this context free category. So, that is why this has become very popular for the compiler design course, and everywhere you will find that we will be talking about this type of languages. Then comes this context sensitive grammar. So, as the name suggests, the context sensitive. So, every rule has got a context. So, context it is like this. So, if I have so maybe I have a rule like alpha x beta producing alpha gamma beta, where this gamma is a alpha beta gamma. So, they are all strings of terminals and non terminals, strings of terminals and non terminals. So, you see that here the thing is that this x can be replaced by gamma only if it is preceded by alpha and followed by beta. So, that is why there is a context. So, the context is that x is preceded by alpha and followed by beta, then only we can apply this rule to change the x to gamma, and alpha beta they remain unchanged. So, they just hold the context, that is why it is called a context sensitive grammar. So, if you have if you are having a string like say a, b, x, c, a, then say x, d like that, and suppose I have a rule which says that b, x, c can be replaced by say f, y, d, e, where x and y they are non terminal and the b, c, d, a, b, c, d, e, f. So, they are all terminal symbols. Now, you see that this rule b, x, c matches with this part. Okay. So, I can replace this part by this right hand side. So, I can from this I can derive the string a, f, y, d, e, but this x cannot be modified because the context does not match. So, here the context is a d, but here it is b c. So, context does not match. So, I cannot do this replacement. So, it remains as it is. Had it been a context free grammar, so like this, had it been a context free grammar, I would have replaced both x's by these rules. So, I could have written like a b and then x replaced by a y z, then c a, then again this x replaced by a y z. So, I could have done like this, but in a context sensitive grammar, since there is a context, so the left hand side has got a context. So, you cannot replace it freely, only when the context matches you can do the replacement. So, it is even better in the sense that you can more precisely frame the grammar rules. Okay. So, that is why this is more powerful than type 2 languages, and type 0 does not have any restriction. So, there is no condition regarding this context, like while writing grammar for context sensitive language. So, you cannot change it from this alpha and beta over the rule. So, you cannot. So, this alpha and beta they remain unchanged from the left hand side to the right hand side of the rule, but if in case of type 0, so that restriction also does not exist. So, there is no restriction on the grammar, no restriction on grammar. So, you can say you can have rules like a, b, c, d producing x, p, q, y. So, you can have some rule like this. So, it is totally independent of this context. So, I am not maintaining the context of this left hand side onto the right hand side, they are totally modified. So, you can have total freedom in writing down the corresponding rules for the grammar. So, this is the type 0. So, type 0 is the most flexible one. As a result, none of the automata they can be used for accepting this type 0 languages. For type 0, we have to revert to Turing machine for designing the acceptor. And as I have said that we will be mostly concentrating on this type 2, because type 2 is the context free grammar and most of the programming language constructs they will be based on type 2. So, we have already seen type 3, which is regular grammar, and we have seen that a regular expression. So, you can always construct a finite state machine for that. For example, for this language you can very easily make a DFA. So, if this is the start state, on A it goes to this state, this is a final state, and on B also it goes to another final state. So, that is a we can draw one DFA which will be doing this operation. Okay. So, this type 3 can be for the regular grammar, and that is for regular expression. So, with this we will be going back to our discussion on grammar. So, grammar, as I have said, that it is a 4 tuple Vn, Vt, P and S. Vn is the set of non-terminal symbols, Vt is the set of terminal symbols, P is a set of production rules, and we have seen that depending upon the structure of P, we can have different types of different class of grammars, different types of grammars. And S is a special symbol in the set of non-terminal Vn, which is called the start symbol of the grammar. And the strings of the language, they will be represented by L, G, then they are the strings that can be derived from S by applying the production rules of from P. Okay. So, any grammar for which we have got for which we have written the production rules, many times what will happen is that we will not be explicitly mentioning the start symbol. In that case, the very first non-terminal symbol that appears in the grammar specification, so that is the start symbol. For example, for this particular grammar, E is the start symbol, because E is the first non-terminal among the set of rules that we have written. For the second grammar also, E is the start symbol. Now, starting with E, you can derive strings like this. So, you can apply the first rule, E producing E plus T, then you can replace this T by T star F. Then you may decide that okay, this F I will be replacing by within bracket E. So, E plus T into within bracket E, and then this within bracket E, that can be modified to say T by applying this rule E producing T. From this you can have E plus T star T producing F. Okay. So, or say not F, say T star F. Then from this thing you can derive like E producing E plus, oh, deriving is already there. So, E plus T into T star I D. From this T can be again be replaced by say F, giving us E producing T star F star I D, giving E producing T star I D star I D, giving E producing part is not necessary. T this T can be replaced by F star. Oh, sorry, this was E plus. So, this E plus part is there, F star F into I D star I D, then that can give us E plus, this F can be made to give an I D, then this E can be made to give a T plus I D star I D. So, this T can be replaced by F. So, you can get it like this. Then this F can be replaced by I D. So, I D plus I D star I D star I D. So, where I D is an identifier. So, maybe I have got an expression like 2 plus 3 into within bracket 4 into 5. Okay. So, this shows the derivation starting with the start symbol of the grammar. So, finally, we could derive this string. So, this string since we could derive this string using the grammar rules. So, this string belongs to the language accepted by the grammar. So, this appears to be very cumbersome. However, the whole process is automatic. So, once we can write down a piece of code that can do this transformation by suitably selecting the rules from the grammar, then the whole process can be automated very easily. So, this compiler, this parser designing task or the knowledge that we will gather during this parser design discussion. So, that will help us to design this type of automated tools. So, coming to the error handling. Now, one also it is very common that the input specification that is given, the input file that is given for parsing, it has got some errors. So, particularly they are written by for programming languages. So, users are writing programs and programmers often do mistakes. Okay. So, those mistakes can lead to different types of errors. First one is the lexical error. So, lexical error are those errors which are which do not constitute any valid word of the language. So, for example, if I have got say if I have got say a one symbol that that is a 2f. So, 2f so this is not valid because it does not fall into any of the regular definition for the language. So, that is a lexical error. Then we have got syntactic error. So, syntactic error means there is some grammatical mistake, like say if then else statement, it says that if some condition then some statement else some other statement, say S1 and S2. Now, if I have not put this then, so if I have written like if C S1 else S2. So, as far as the lexical analysis tool is concerned, so it will identify these individual tokens, if, else, then the tokens that will constitute this condition, tokens that will constitute the statement. So, it will find those tokens, but when it comes to the syntax analysis phase, so it will be taken as a, it will be detected as a syntactic error, because this does not make a correct statement of the language. So, it does not follow any grammar rule. So, that is the syntactic error. So, another class of error are the semantic errors. So, it is the program is or the statements are syntactically correct, but semantically there is some problem. This is particularly visible for the programming languages where the variables have got some types and the types are all predefined. So, for example, in the language C, so if you have got an assignment like x equal to y plus z, then this x, y and z, they must be predefined variables. So, in your program you must have defined somewhere, for example, integer x, y, z, that must have been declared somewhere. So, if this is not there, then x, y, z will not be there in the symbol table, and when parser will try to parse this thing, so lexicon analyzer will return x as id, y as id, z as id. So, that way it is an expression id plus id, then it is an assignment statement, everything is correct, syntactically it is absolutely correct, but I cannot derive the type of these variables, and whether this plus operator is applicable on y and z, that is also not known. For example, if y and z are say character arrays, then y plus z does not have any meaning. So, these are semantic errors. So, these semantic errors are also serious and they are to be detected, but that is not a grammatical error, because grammatically it is correct. Grammatically we have got this identifier plus identifier. Now, meaning of those identifiers or the types of those identifiers will tell us whether the construction is semantically correct or not. We have got semantic errors, then there are so of course, the lexical errors are there. Now, how to do error handling? So, error handling means somehow the compiler, so it should detect those errors, and not only that, the detection, so it should tell the user that okay, here is the error. So, it should pinpoint the error, like what is the error and at which point in the program the error has occurred. So, error handler, it will have the goals, like it should be able to report the presence of errors clearly and accurately. So, that is the first thing, that some error is there. So, what is the error and at which place? So, that should be told very clearly. It should be able to recover from each error quickly enough to detect subsequent errors. So, as I was telling in some classes earlier, that error handling is important, because if you detect one error, and if you just on detection of the first error, if the compiler quits the compilation job and it asks the user to correct it, and maybe user will correct it and then give it for compilation, just to find that after 2-3 lines again there is another error. So, typically compilers work in a fashion in which it produces all the error messages together, so that user can correct all those errors and then give it for compilation. So, but for doing that it is very difficult, because particularly for syntactic error, since this compiler or the parser is working based on some automata, it may go to a state from where it is very difficult to come to a clean state. So that is a very important job. So somehow the compiler must be able to decide that okay, I have to discard next few tokens and come to a state which is clean, and I can start looking into the new tokens from that point. For example, most of the programming languages, so they have got the feature that any statement that you have, it ends with a semicolon. Now, while doing the parsing operation, so suppose there was an error at this point, okay, then somehow the compiler must skip through all these tokens and it should come to the next semicolon, and from this point onwards it is expected that the effect of that error is gone. Okay. So, from this point onwards the compiler should start doing the parsing afresh and try to see whether it can detect more errors or not. So, if the recovery is not proper, then the compiler will produce arbitrary error messages that will mislead the user. So, this is very important that the compiler can come up to a decent state from which it can produce proper error messages for the subsequent errors as well. So, it should add minimal overhead to the processing of correct programs. So, if the program this error handling part, so it should not be such that it creates the code it makes the code generation process for correct programs to take long. So, it should not happen like that. So, the compilation should be fast, at the same time it should be able to decide on those errors, okay, and it should be able to recover from there. So, this is a very important thing to do. So, we will see how this can be done. There are several error recovery strategies followed by these compiler designers. One is known as panic mode recovery. So, panic mode recovery is like this: suppose we are at some place and there is a crowd, and in the crowd there is some sort of news comes that something has happened, maybe there is a fire or something like that, then everybody wants to come out of the building, for example. So, if the people are inside a building, all of them try to come out, and we say that is a panic mode. Maybe it is not mandatory that we should come out so early, but most of the people will all the people will do like that. So, this is known as panic mode recovery. So, what the compiler does is that it will discard input symbols one at a time until one of the designated set of synchronization tokens is found. So, what is a synchronization token? So, as I have said that depending upon the programming language, you can define when a particular block ends. For example, for the C language, so you know that say every statement ends with a semicolon. Now, if discarding up to semicolon is also not sufficient, you find that still the compiler the parser could not come to decent state, another synchronization token is the closing brace. Like so normally whatever we have, so every block of statements, so that is enclosed within a brace, pair of brace. So, if there is some error in this statement and by discarding this statement we could not come out of the error, then what the compiler will do is that it will skip the successive statements also till it comes to the brace, so that it has skipped an entire block. So, that is one possibility. So, some programming language, so they will allow you to have individual procedures and the begin end block markers, begin procedure, end procedure markers. So, in that case the compiler can skip up to that point. So, depending upon the programming language that for which we are designing the compiler, so we have got different types synchronization tokens. By analyzing the program, we can understand what are the synchronization tokens. So, this is known as panic mode recovery. Then there is a phrase level recovery. So, phrase level recovery, it will try to replace a prefix of remaining input by some string that allows the parser to continue. So, some part of it maybe there is so there is something like this. For example, suppose my my language says that there is an if then else statement, if condition then statement, else statement. Now, it may so happen that this then token is then this then part is missing. So, what will happen, the parser or it will see this if part, condition part, then it will see the statement part. So, what the parser can do, so it can intelligently determine that here what is missing is a then token. So, it can insert this then token into the input stream. So, that way it will replace a prefix of remaining inputs by some string. So, this is the remaining string from this point onwards. So, this is the remaining string. So, it replaces this part by this, it introduces this then at this point. So, the program did not have, the program that we are considering has got something like this, if C S1 else S2. So, this part is not yet seen. So, it has got S1. So, it will understand that this I have to put a prefix then at this point, then the whole thing will become meaningful. So, this is the phrase level recovery. So, it tries to introduce some phrases at the beginning of this input part, and then it can continue. So, this way we can have different error recovery policies. Okay. So, there are error production and global correction that we will see in the next class.